Hello everyone. So this paper is about model-agnostic meta-learning for faster adoption of deep network. This is from ICML 2017 paper and authors are Charles Huffin, Peter Abel and Sagi Lavin. I am a student of Masters of Artificial Intelligence presenting this paper for Advanced Machine Learning course. So let's start with the initial understanding of what is meta-learning. Which is usually called fewshot learning as well. So the purpose of this meta learning is to train model on variety of learning tasks such that it can solve new learning things on which can actually able to learn on while we can train only small number of samples and still that performs and identify classify able to classify really good on the basis of number of gradient steps. So this way, this approach is actually uh, present really good results in few-shot regression and accelerate the fine tuning. So here you can see on slide that while machine learning we only provide one or two which is usually called few sorts few samples of training label data so that it can train and and actually some gradient steps are applied which we will see further how this approach is applied to learn it better in the case of classification regression and IL reinforcement learning. That way, this paper is actually using MAML, model agnostic meta learning. That way, it really gives good results. Let's see why we acquired this meta learning. Meta learning is really fast because IL task is taking too much time in training, and as we know, machine learning is whole about the process of mimicking human learning. So here we want to learn the way that humans learn, like they learn in real life, like they see one or two things and they are able to identify things very well. They once play a game and they are able to play it very well. That way, we want our model work. So we acquired this meta learning. Let's go to paper after understanding what's meta learning and few-shot learning. So what it's applying? So actually, it's pre-tuning the network, ImageNet classification, and then fine-tuning the network on new tasks. So these tasks are very few in sample, not too much, and also enables the neural network to learn new vision tasks, usually relatively on small data set. The whole purpose of this paper is using the few-shot learning, so it not takes too much time. This work because we have a huge labeled image data set already in the somewhat consistent, and that is reused with the approach of gradient steps, and that is again applied to this learning. Now we will see how do we bring initialization and meta learning for non-vision domains, like that is a different approach, and that can be seen in other tasks and future related things. Here we will see how model agnostic meta learning work. So there are multiple tasks. Theta is here parameter which we can fine tune while training, and this is whole meta learning. This shows how meta learning is going, and this dot is showing the learning and adaptation after that parameters is fine tuned while training on a small data set. So this diagram is actually model agnostic meta learning algorithm MAML. So the paper is using this approach, and this way it optimizes the representation of theta, and so that with the help of that theta it can quickly adopt the new task. This is first algorithm. There are three algorithm which is one by one improved with applying different things, different approaches. So this is the simpler form of meta learning. After that, we will apply that on classification. After that, we will apply third algorithm. We will apply on IL, information learning. So first, this apply that this algorithm. Let's see how it's working. So first, we will require distribution of over tasks. So we will have different tasks, and we will distribute it properly. And we will acquire alpha beta, which is hyperparameter, is which initialized with theta. With this way, we can fine tune some parameters. So we will apply that while loop on whole the batch of data. Sorry, task is divided in ti to complete different distribution tasks. Every task is evaluated with the respect of k examples, which is actually adapted during the parameters with gradient descent. So this gradient descent is really important, because this is already have the learnings which is applied here, adapted during this, and applied here with the help of theta parameter. And when all these tasks are updated with the help of k example computed gradient descent, then in last we will update the parameter too. And this algorithm will continue on all the tasks and end in last completely. So we need to understand why this is required, and how this can actually help the if there is any test error, then it actually samples that TI task in training error of meta learning process, and that way a task used for meta testing are held out during meta training. So we will move to next algorithm, that is for supervised learning. So as I earlier said, there are three algorithm which is improved one by one. Now we are applying MAML for fewshot supervised learning. So there's a distribution over tasks similar to earlier, and this is also, but the 5 to 8 steps are changed. Like earlier, there was only 2 steps. First, we evaluate the task with k example, then we compute it with the gradient descent. In here, with supervised learning, what we are doing, we are actually adding first k data points. They and k data points are using here and evaluating with the help of the earlier task and theta parameterization. The gradient descent parameter approaches we are already applying here, and then we sample these data points with respect to the earlier computation. And after all these tasks are updated, we are also doing updating the parameter theta here, using the data points of task which we learned earlier. So next we have to see how this approach improves the thing in ML, and pre-trained. These are pre-trained steps which we are using in the form of gradient descent, and this is Oracle. Oracle is actually in this paper. It's defined like it's a pre-task which can be used to compare in the form of different things. So that way we can use it, and that is Oracle actually receive the identity of the task, and we use it in comparing for all the performance and comparing the things. This graph actually shows the mean squared error with the with the comparison with the number of gradient steps, and that results showing the learning curve at meta testing time. And MIM will continue to improve with additional gradient steps without overfitting to extremely small data set during meta testing, and achieving a low that's substantially lower than the baseline fine tuning graph. That way we can see here that with the help of k-sort regression K10, we the MAML approach, this paper approach is performing and learning really good way. Going to next slide. Oh, this one, reinforcement learning. Earlier we seen basic MAML, then in next we supervised with supervised learning. Now we are seeing with reinforcement learning. Now, in reinforcement learning, main changes here k trajectory of data points. That with the k trajectory of data points with on the basis of ti task, that is changed, and on the basis of this evaluation, this computation of gradient descent is also changed, and sample trajectory are. So in earlier approach we were handling the data points, and now here we are handling the k trajectory of d x1 a1 xh. This way, reinforcement learning can be applied, and all other steps will be similar to that. And in last, also we will update that theta parameter. Now we will see how IL experiment is done and how this will be changed on the different approach and how this is gone to it. These are random, Oracle, pre-trained MML. So it actually results the half cheetah and ant locomotion task with the task one on the far right. Each candidate step require additional samples from the environment, unlike the supervised tasks. This result shows that MAML can adapt to new goal velocities and directions substantially faster than conventional pre-training or random initialization, achieving good performance in just 2 or 3 gradient steps. And authors actually exclude the goal velocity and random baseline curves since the returns are more worse here in this case. So here we can see how IL experiments are doing really good on MAML in this approach. These are the experiment results shown by authors on the paper, and how they are showing how their performance. This is the first approach, first order approach, also first algorithm we have seen, and this one is last third approach, third algorithm on reinforcement learning. Here we can see similar performance improvement over it from other papers. They are comparing with the Siemens net, matching nets, neural statistician, and memory mode. All these are paper presented before them, 2015, 16, and 17, and that way, this whole comparison is done. In last, we can see how limitations and future improvements are done. So performance is dependent on gradient based training. So if gradient based training is actually not able to learn well with the parameters, then the model performance might not be good. So it's dependent on that gradient based learning. These experience can be tried out and extended with also geosort learning. This can be future enhancement. Also, authors suggested that the future work can be multitask initialization, standard gradient in deep learning, and reinforcement learning. So all this can be happen with the help of fewshot learning and MAML approaches discussed here. Thank you so much.